Hi, everybody. Thank you for joining us for another EI Live K-12 session for students and educators, a series from the Columbia Climate School. My name is Adrienne, and I will be facilitating the session today. For those of you who are unfamiliar with the Columbia Climate School, or if you're joining us for the first time, we are a new school at Columbia University for cross-disciplinary climate research. The school uses the university's strengths in basic and applied sciences and expands its resources to understand climate and its impact in society. The Climate School is the first new school at Columbia in over 25 years, and it incorporates the entire Earth Institute, which includes the Lamont Doherty Earth Observatory, along with more than 20 other centers and several hundred people who collaborate among many departments across the university. What we're doing with these EI Live K-12 sessions is to introduce you all to our work through our scientific experts. These bi-weekly sessions run throughout the whole semester, and if you would like any more information about these sessions, please don't hesitate to contact us. Each week, we'll focus on a different topic and will be directed towards a certain age range. So today's session is how do we know the temperature of the Earth? We're going to learn about the history of global mean temperature calculations, discuss how scientists calculate changes in the temperature of the Earth, and discuss the data that has been used to calculate the temperature over the past 150 plus years. We're joined by Nathan Lenssen, a PhD candidate at the Department of Earth and Environmental Sciences. We will have time for questions at the end, so please use the Q&A box throughout the session. And now I'm just going to turn it over to Nathan to get started.
Great. Thank you so much, Adrienne, for having me here, and thanks to the Climate School for supporting this work. So yeah, as Adrienne says, my name is Nathan. I'm a PhD candidate at Columbia and at the NASA Goddard Institute for Space Studies. And before I hop in, I said we have a really reasonable sized group today, and I'll have the Q&A open throughout my talk. So please throw in questions whenever you want, and I'll try to answer them as I go along, as well as at the end. And so I live in Manhattan, and actually many of you may or may not know, but there's actually a NASA lab in downtown New York in Manhattan, and it's actually in this building above the famous Seinfeld diner sign, which is a pretty fun fact. And so a lot of this work that I'm going to be talking about today, and a lot of the science that's gone on in understanding global temperature and climate change, has happened in this building above the famous Seinfeld sign. And so many of you are here very likely have followed the news on climate change and global temperature, and just probably have seen the annual New York Times headline or headlines in other papers about hottest years that have been tracked over the past few years. And so just to throw up a few headlines, we had kind of hottest years in 2012, in 2015, in 2016 with the large El Nino that year, and a kind of a tie in 2020. So just to say, like, there's been a lot of attention and increasing attention in terms of the global mean temperature in this past decade, and we continue to expect to talk about this a lot in the coming years as climate science and policy continues to advance. And so what I'm going to be talking about today is this graph. We're really going to be focusing on how science and the scientific community has gotten to this graph. In particular, we'll be talking about, on the x-axis here, we have the year. We're going from 1880 up until present. And on the y-axis, we have the temperature anomaly, or the difference in temperature in degrees Celsius from some normal or average temperature. And today I'll be talking about both how we calculate these black points, or the annual temperature anomaly for each year, as well as these gray error bars around it, basically the confidence we have in these calculations. And so that brings me to the title of my talk, of how do we take the temperature of the Earth? How do we go from sticking a thermometer up into the air to creating this graph that summarizes really the global climate system? And so really, to cut to the chase, so you actually know where I'm going, I'm just going to give you the 3 steps of actually how we calculate the temperature of the Earth first, and then I'm going to go into some details of why we care about this, and some of the more specifics about why this is a tricky and interesting problem scientifically. And so for calculating the Earth's temperature, we get our raw data from mostly, at least over the land surface, from thermometers. That is, thermometers sitting on weather and climate stations all around the world. But we don't have measurements everywhere. As you can see, we only have so many measurements in Africa and South America, but we want to kind of get the estimate of the temperature everywhere. And so that's where the work that is done at NASA and other places comes in, and we have to take these thermometer measurements and combine them in some useful way to calculate the temperature everywhere on Earth. And then once we have an estimate of the temperature everywhere on Earth, it's as simple as taking the average of all these temperatures to get some sort of global, to get the global annual temperature curve. And so this is just the quick run through of these 3 steps of moving from temperature data to estimating the temperature everywhere to taking the average of that to get the global temperature. But we'll talk a little bit more throughout the hour on why this is interesting. And so I've kind of come up with a few motivating questions for today that I'll answer throughout these 45 minutes. The first is taking a step back and thinking about some of the physics at play here and asking the question, why do we actually even care about the global mean temperature? What does it mean for our climate system? The second question is why is calculating the global temperature difficult? And I gave you a little bit of a preview of that already. And to answer this, I'm going to also answer the question, what is an anomaly, or in this case, a temperature anomaly? And also show some results that answer the question, how well do we estimate global temperature when we don't have stations everywhere? And then finally, I'll compare this calculation that we're doing at NASA to some other calculations in other parts of climate science and answer the question, how do we know the global temperature calculation done by NASA is accurate? And so first off, this is just going back to, this is going to be a little bit of intro atmospheric science and really, why do we care about the global mean temperature? And so to talk about this, we're going to talk a little bit about Earth's energy balance. And so the Earth is this wonderful physical, chemical, biological system that is a really exciting place to be a scientist. And it gets all of its energy, all of its incoming energy from, or most of its incoming energy from the sun. It gets a little bit coming up from the surface as well. And so if we're thinking about our Physics 101 class or our Physics 1 class, we think about, anytime we're thinking about energy balance, the first step we remember to learn how to do is to draw a box around our system and think about the energy coming in and coming out of the system. And so in the case of our Earth system, we have energy coming in as the rays of the sun, and then we also must have some energy leaving the Earth system. Otherwise, we would just kind of keep heating and heating and heating. And so the energy coming in, like I said, is radiation from the sun. But we also have energy leaving the Earth due to the Earth's temperature. Basically, the Earth is also radiating out energy. And so we know that we must have equal energy, or approximately equal energy, coming in and out of the system, because, say, for instance, we had more energy coming in than leaving. From remembering our really basic thermodynamics, if we have an imbalance of energy, we have an increase in temperature. And that would lead to an Earth getting hotter and hotter until it eventually just kind of melted or burnt up. And so now we're taking a look, instead of looking at the Earth in the sun system, we're now kind of standing looking at the Earth's surface. So down at the bottom of the screen, we have the Earth's surface, or the land. And then in the middle here, we have the atmosphere. And then up top, we have space. And so this is the same energy coming into the Earth system from the sun, as shown by this yellow arrow. And what this energy is doing is it's passing through the atmosphere, heating up the Earth's surface. And then because the Earth's surface is warm, it's going to radiate out energy as well. And like I was talking about on the last slide, we expect that these to balance out pretty much exactly, keeping the temperature of the Earth constant. But why this is really important, and especially in the context of talking about climate change and greenhouse gas emissions, is that this simple model doesn't really talk about what the atmosphere is doing. And so if we had an atmosphere without any greenhouse gases, basically any gases that trap radiation inside the planet, what we would see is that energy coming out from the Earth's surface would just pass straight up through and exit. However, if we have an atmosphere with greenhouse gases, which we do regardless of humans or not, we would have the atmosphere actually absorbing some of this radiation coming up from the Earth and warming up and then emitting radiation itself. And so then the atmosphere is radiating energy up, but it's really critically also radiating energy down. And so now you can see that compared to this first picture, where we don't have any radiation, we only have radiation coming down to the surface from the sun, we now have kind of additional radiation coming down and increasing the temperature and warming the surface more. And so this greenhouse effect is really critical actually for making Earth habitable, for making the planet have a temperature that is livable for us. But we're seeing the consequences of increasing the greenhouse gases even further right now. And so if we increase the amount of greenhouse gases, we'll see that the atmosphere has absorbed more energy and it's re-radiating this energy down, causing the surface to warm. And so why this is really useful, this like simple energy model is really useful to climate scientists, is because the average global temperature is really tightly tied to how much radiation the atmosphere is absorbing, and therefore the amount of greenhouse gases in the atmosphere. And so by looking at the global surface temperature, we're able to kind of keep a tab on the whole energy balance of the Earth's system. And so just to pull up some data to show how coupled CO2 and global temperature are, this is a graph from NOAA's climate.gov site. And in the gray line, we have the time series of atmospheric CO2, as shown by this y-axis over here. And in the colors, we have the global annual temperature anomalies. And as you can see, and has been shown with way more sophisticated science than this, but just kind of like glancing at this if you squint, we see that these two curves really mirror each other very closely. As CO2 increases over time, we also see an increase of temperature. And so this was just a really quick recap of global mean temperature and why we care about it, and why it matters for climate science and climate change science in particular. And just as to provide a really succinct answer of this, global mean temperature allows us to track global atmospheric change and really global Earth energy budget. And so now I'm going to move on to the second question I posed for today is, why is calculating the global temperature a tricky problem, or why is it difficult? And so here is a map of the annual average temperature on the planet. And so this is just if you take the year-round average at each location, and this is the value of temperature you get. And if we had more time, if we were in a classroom, we would take some time to discuss maybe in small groups or as a class about patterns that we see emerging on this map. Some common answers that I get is that it's warmer in the equator, it's colder up at the poles. I then kind of generally pry for information about smaller scale patterns these students see, and where they might be getting this information, and or what they think might be causing those patterns. And really the goal of that is to get students to think about the role of mountains in these pictures. So in particular, we notice that the Andes, the Rockies, and the Himalayan mountains these regions have much colder average temperatures due to their higher altitudes. And the other thing I really like to highlight on this figure is just that how complicated these patterns are. Sure, we have a general pattern of warmer near the equator and colder at the poles, but there's tons of really intricate variability that you notice with temperatures changing many degrees in just a few hundred kilometers in certain regions, like in the equatorial Andes. And so as I mentioned when I was setting up this problem, our goal in estimating the global temperature, that intermediate step is actually estimating the temperature at every place on Earth. And if we don't have measurements at every place on Earth, you can just imagine how hard it would be to, with limited data, reconstruct this whole map. And so that's why GISTEMP, the NASA's Global Surface Temperature Project, and other surface temperature products generally model things called temperature anomalies rather than surface temperatures. And so I haven't discussed this yet. So the natural question is what is a temperature anomaly, and why are they useful in this case? And so in plain English, before I go into some of the math and show some figures, a temperature anomaly is a description of how much warmer or cooler a location is than normal, with an emphasis on that normal. It's really a relative comparison of temperature to some sort of normal value. And so just writing this same English up as an equation, we have our temperature anomaly equals the observed temperature in degrees Celsius minus some sort of long-term average. And so just tying this back to our maps, I didn't have time to show this simulation today in the middle, but our anomaly, this map I just showed, equals some observed temperature map, which you can think of as like a weather map, minus a long-term average. And you'll notice that when we're looking at the anomalies, they are centered at 0, meaning that we in general see an anomaly of 0 or average, and then they range from maybe positive, in this case, a little 7 degrees to -5 degrees. So variations around normal of plus or minus 5-ish degrees. And so these are, you might kind of already notice that these anomaly charts look kind of different than these average temperature charts. And I'm going to talk about a little bit why and why they're really useful in this problem. And so to do this, I'm going to bring an example in from my home state, Colorado. And Colorado has some really interesting geography and geology with the Rocky Mountains running through the western half of the state. And so I've picked 2 locations in Colorado that have long-running weather stations where they've been collecting temperature data for decades. The one in black is in Denver at the Denver International Airport, and the one in blue is in Crested Butte, a really pretty place up in the mountains. And so just to show a little bit about the kind of the local geography of these 2 places, Denver is located in an elevation of around 5,000 feet. And where the airport is looks a lot like this. This is one of the highways out towards the airport. Whereas Crested Butte is almost 4,000 feet higher in elevation and is in a really mountainous region. And so here again would be a chance where I would ask the audience kind of what we expect of the relative temperatures in these 2 locations. And to cut to the chase here, we see that even though these are only 125 miles or 200 kilometers apart, we see that Denver has a mean temperature of around 10 degrees Celsius over the past 150 years, as shown in this annual mean temperature time series. But Crested Butte has an annual mean temperature of around 0. So the difference in mean temperature is almost 10 degrees, even though these locations are so close. And so why this is a problem when we're trying to understand how temperature varies is imagining a very real problem that we have to do is kind of predicting the values at one station from another station. And so now I've put the 2 time series up for these locations on one graph. So up here in black, we have the annual mean temperatures in Denver, Colorado. And you can see, again, they're located right around 10 degrees Celsius or 50 degrees Fahrenheit. And we have the annual mean temperatures for Crested Butte. And it's amazing that we have this much data in a place as remote as Crested Butte. But let's say that we wanted to know the temperature in Crested Butte back in 1880, when we start doing our calculation of global mean temperature. Well, right now, Denver is not very useful at calculating the Crested Butte temperature. We see that they're kind of in totally different places on this graph. It really is hard to see how Denver could provide us any information for how the temperature in Crested Butte varies. But this is where temperature anomalies come in. And so if you remember, the idea of a temperature anomaly was taking an observed temperature like we have here and subtracting out some kind of temperature that we expect, or some average temperature. So to illustrate that concept in these two time series, in these two locations, I picked a time period when both of them have pretty consistent data. And so that's shown in these red lines here. So you can see that I picked, I think, about between 1950 and 1980, both of these stations had almost data in every single year. And so we can see that as I had said on the previous slide, Denver has a mean temperature of right around 10, and Crested Butte has a mean temperature of right around 0. And so now if we calculate the temperature anomalies of these two stations, we basically take each one of these data points and subtract the value of the red line from them. And some really magic happens. All of a sudden, these two time series look really similar. So you notice now the y-axis label changed a little bit. We're now talking about the annual mean temperature anomaly. And we see that these two stations really have a lot of the same variability, meaning when the temperature anomaly in Denver is positive or is higher, the temperature anomaly in Crested Butte also tends to be high, and vice versa. And so now this is really useful because we can use the information in Denver to help us estimate what the temperatures in Crested Butte are when we don't have data. So for instance, in this time period around 1980, we can predict that Crested Butte might have followed a similar up and down zigzaggy pattern. And we have pretty strong evidence that that's the case because how closely these two time series align in the rest of the record. And this property of anomalies that they're really related when the distances are pretty close actually holds throughout the whole planet. And so we saying this in English, it's in like kind of a sort of mathy English sentence, temperature anomalies are very simulated or very correlated for locations that are close, even if the actual temperatures are very different. And so we can see this on maps then. This was the first map we were looking at of annual average temperature. And here in some places, temperature is correlated in space, like in the Amazon. But if you get to the boundary of mountains, like we were just discussing out in Colorado, temperature was not correlated in space. We had kind of very high swings in temperature, very large differences in temperature over space. However, if you look at the map of temperature anomalies now, this is from NASA GISS's product. You can see now that this field looks very smoothed out, meaning that if you have some information in one point, you'll have information from a large range of space. And this is really a kind of hack that scientists discovered back in the 70s and 80s that made calculating the temperature everywhere on the Earth, or at least estimating the temperature everywhere on the Earth, really possible. And the upshot of this, or what's really neat for this problem, is that we can use just a few temperature measurements to estimate the temperature everywhere on Earth. And so just to tie this back to this diagram, this is really the calculation that's done from step 1 to step 2 here. We take temperature data from thermometers that's measured in degrees Celsius or degrees Fahrenheit. We calculate the anomalies, and then we use those anomalies to estimate the temperature everywhere, as is shown in this map right here. And if you're thinking right now, well, this is a lot of like hand waving, like, does this really actually work? And so the answer to that is yes, quite well, but I'm actually going to do better and show you some figures and talk to you about how we actually, as scientists, have shown how well of a job we do at estimating global temperatures when we don't have those thermometers everywhere. And so as an example, here I have up the distribution of station locations in the 1880s. And so, excuse me, here I've colored them by their observed temperature anomaly in some year. And so we can see that back in the 1880s, in that decade, we really only had measurements in the United States, in in Europe, mostly Western Europe, in India, and in kind of just around coastal Australia. And there's a few other stations dotted around, maybe in kind of East Asia, in like one in Africa, a couple, they're in white, so they're kind of hard to see, but a couple down in Southeast South America. But we really only have stations in a few parts of the world. And so what me and a few scientists at NASA did is we asked the question, okay, so let's now try to determine how accurate of a job we can do by calculating the global temperature with just this amount of information. And so the secret to doing this was we took really high resolution, meaning really fine scale, output from a climate model that simulated the Earth's climate very, very realistically. And so with that, we're able to get a kind of a fake temperature field of what a temperature might look like everywhere. And so this is model simulated temperature anomalies across the whole land surface. And so here, this isn't like really observed temperature data, but we know that it looks very similar to how the Earth's temperature actually does look. And so what we just did here is we say, okay, well, when we have data everywhere, it's really easy to calculate the total global temperature because we just take the average of all these points. So let's calculate the true temperature. And then let's go back to our really limited information and use this amount of information to calculate the temperature and then compare them and see how good we did, see how accurate we were. And so as I said, how GISTemp and how NASA actually calculates these global temperatures is they take each one of these station locations and they kind of say that, okay, each station describes some area around it. And so how this looks on a map is when we take each of these stations and extrapolate out from them, we get a map that looks like this. So I'm going to flip back and forth a few times just so you can see. So you can kind of pay attention to these stations up in here, might be an easier place to see it. So here we have stations throughout Russia, and with the GISTemp procedure, we know that these stations kind of describe a range of around 1,000 kilometers around them. So when we put that into a map, we get something that looks like this. And so this gives us a lot more coverage, but it still doesn't of the land surface, but it still doesn't give us coverage everywhere. And so to just kind of highlight how much coverage we're missing, I now put areas in gray where we don't have coverage from the stations in the 1880s. This is like over 50% of the land area. So we're still really missing a lot. But what's neat is then now we can compare the global mean that we'd calculate from this map with the global mean that we would calculate from this map and take the difference and see how far we're off. And since this full field, this model simulated temperature field came from a model, we can actually do this many, many times on many different kind of data points from this model simulated temperature data set. And when we do that, we can get a distribution of the air. So this graph I put down in the bottom left shows on the x-axis the air that our method has at estimating the global temperature. And so these bars have height depending on how many times we saw that amount of air over the data set. And so we see that this distribution is centered right around 0, meaning that on average we have 0 air, but it has a pretty, it has a spread. We have some amount of spread, meaning that we're not always exactly estimating the global temperature correctly using our method as we expected. And luckily for us, this distribution that we get looks kind of like a bell curve, or actually remarkably like a bell curve. And we're able to use some basic kind of normal statistics then to estimate the uncertainty. And to do so, we got lucky and we can just take the standard deviation and use that to quantify how much air or how much uncertainty we have in estimating the global temperature. So in this example right here, we can see that we have a standard deviation of about 0.2, which leads to a 95% confidence interval of around 0.4. So that is, we have an estimate back in the 1880s of the land surface temperature up to about plus or minus 0.4 degrees. And so when we combine that with a similar analysis that we also have to do over the ocean, which I don't have time to go over here. This was just for land. We're able to get the uncertainty over the entire global temperature series, as shown by this gray. And this is really, really neat, because uncertainty in science is not something we're trying to necessarily eliminate. It's really something we're trying to understand, because it allows us to understand how strong of conclusions we can make looking at our data. And so when we go and we know there's uncertainty in these estimates of global temperature, and when we go in and calculate them, we see that the observed warming since 1960 is just much, much greater than the uncertainty in our measurements. And so calculations like this are really important for understanding how confident we can be in our scientific and other claims made with this types of data. And so just to summarize this, small uncertainty, as shown here in the gray, scientifically is really just saying that the global station network does a great job of estimating the global temperature, even as far back as 1880, which is just still pretty remarkable to me. It's this like how well this method and math and science works. And so I'm really zipping along. So I certainly will have some time for questions. So please throw any questions in the chat as I talk through the final portion of my presentation. And so, yeah, the last part I wanted to talk a little bit about is go into a little bit more detail about how do we know the global temperature is accurate. And so I've talked a little bit about tests we've done on the data and the methods for calculating the global temperature. But there's also other ways that people have investigated the accuracy of the global temperature record. And so the big strategy for this is comparing GISTemp, or the NASA Global Surface Temperature product, with independent data, meaning some other estimate of global temperature that doesn't incorporate any of the same data as GISTemp. And so today I'm going to share two really key comparisons that have been made that gives us a lot of confidence in the accuracy of our conclusions that we can draw from this GISTemp global temperature record. So these are climate models or physics-based simulation of the Earth's climate. And I'm going to be showing some results from CMIP-6, or the Coupled Model Intercomparison Project, which is the huge worldwide simulation study that's done by all the climate modeling centers around the world. And then I'm also going to show different results from a different study that compared the surface temperature record as calculated by thermometers with satellite data. And so as I said a little bit, but climate models, what I mean here is physics-based or dynamical climate models are some of the words that are used to describe these. And how these climate models work is the Earth is chopped up into a bunch of tiny cubes. And for each of these cubes, we know the temperature and the humidity and the wind speed within the cube. And then nothing else is given to the climate model other than the physical equations that govern the system, meaning that all of the wind, all of the temperature changes are just totally generated by physics. And so there's been just an enormous amount of resources in terms of science and computing in developing and running these models to understand how the Earth's climate has and will continue to evolve in the future. And the latest of these, over I think over 40 or over 60 of these models were run around the world, and created this this very messy chart. So I'm gonna talk through this quickly, but I want to just orient you to a few things on it. In black, we have GISTemp, which is the NASA surface temperature product I've been talking about. And in red, we have the multi-model mean, which is the average of all of these runs shown in all the other different colors. And so what's pretty remarkable is that what has been observed in black very closely follows the pattern of what has been observed in these model simulations. And in addition, the observations in black are fully contained within the uncertainty of these model simulations. And so kind of restating this, I wrote this out so you can read it if you're more of a textual learner like I am. Note that GISS temp, as shown by the solid black line, is very close to the average of all of the models, the solid red line, and it also falls within the uncertainty, meaning all of these kind of envelopes around show the different spread from different uncertainties in the different models. But GISS temp and what we've observed really falls within. So this is an exciting result. It shows that if we sit down and just use physics and our knowledge of the Earth system to simulate what the past 150, 200 years looked like, we get a result that looks quite similar to what we actually observed. And so this is kind of both a check on how good our climate models are and how good our climate data is. So it's a little bit kind of working both ways. So luckily I came prepared with a second source of evidence for why we really have a lot of faith in our observed temperature record, and that is from satellite data. And so up here in the top right is a artist's rendering or a fake picture of this satellite that NASA put up in the early 2000s. It's the Aqua satellite, AQUA, and it has the AIRS instrument on it, which is, I don't remember what it stands for off the top of my head, but basically the AIRS instrument is a very high resolution infrared camera that's basically just like a big thermometer pointing down at the Earth, and it can measure the surface temperature of the Earth with a little bit of math involved. And so critically, this is a completely independent calculation of the Earth's temperature from any of the data used in the calculations I've been showing you thus far. And so what was really neat in a 2019 paper is that they calculated the surface temperature over the past 20 years according to the satellite and compared it with GISS temp as shown in the teal curve. And so red is the satellite here, and the rest of these are kind of thermometer-based calculations. And we see that their variations are very similar, if not indistinguishable. We see that even the very small scale fluctuations like were shown in the 2006 to 2008 period are captured with the AIRS instrument. And so to say this in words again, the GISS temp global temperature as shown in the solid teal line is very, very close to the totally independent AIRS satellite estimate as shown by the solid red line. And so just to put these all up on one slide, these are really two totally different principles for checking the global temperature work, and they both have quite high agreement with what we're seeing from GISS temp and the calculations we're making from thermometers. And so just as a recap, I have the motivating questions for today and some short answers. So in asking why do we care about the global mean temperature, and really it's because it measures the energy balance of the global climate system and allows us to kind of keep tabs on how changes in the atmosphere are changing that energy balance. Second, why is calculating the global temperature difficult? And one of the biggest reasons is because we don't have stations everywhere on Earth. But as I showed, we're able to quantify how good of a job we're able to do with those limited stations. And in fact, we're doing quite a good job at estimating by using surface temperature anomalies rather than the actual temperatures. And then finally, how do we know the global temperature is actually accurate? And I've kind of shown you two comparisons by comparing with physics-based climate models and as well as comparing with measurements from satellites. And so it looks like we have at least 5 minutes, if not more, for questions. I'm happy to hang around as long as there are questions, but thank you so much for listening. There's so much more I wish I could have shared with you all, but I've been happy to discuss anything about global temperature and climate change and variability. So thanks for your attention today.
Yeah, so we have a few more minutes. If people have questions, just put them in the Q&A or the chat. For now, I'm just going to start asking you a couple of questions. So for one, the chart that you showed showing that like warming since 1960, it seems to have accelerated quite a bit. And so is that primarily because of just increased greenhouse gases in the atmosphere? Is that just, the kind of, I guess, side effects of increasing temperatures? They talk about the oceans getting warmer and the glaciers are melting. Like, is that all kind of seen in that chart?
Yeah, definitely. And there's just so much going on in this chart as well. But really we see that much of the increase in CO2 has happened since 1960. So between 1880 and 1960, we saw an increase of CO2 of maybe 25 parts per million. But then since then, we've seen an increase of now about 100 parts per million, if you go to the latest values on this chart. So we've really seen the explosion in CO2 post-World War II is the biggest thing we're seeing there. But I think something else that your question reminded me of is that we see a lot of wiggles in the temperature. And that's because we still have variations in the climate at play that would be occurring regardless of any sort of CO2 emission or not. And those make it hard to understand how the climate is changing on short timescales, because we expect these wiggles to happen and we'll expect them to continue to happen as well. So thanks for the question.
Yep, great, thank you. And it looks like we have a question in the Q&A from Dennis. Is there an archive of lake ice data? He went to college in Plattsburgh, New York, and Lake Champlain was frozen over every year. In 2006, he went to Burlington in February and the lake surface was mostly liquid.
Yeah, I know there's a lot of different archives of this sort of ice data. One of them that my boss, Gavin Schmidt at NASA, has been tracking is a really big ice breakup, and he's been tracking for the past few decades is I don't know the proper name for it, basically the breakup of ice over the Northern Passage. And so we've seen that's gotten earlier and earlier. So I'm guessing that would be similar to what's observed in Champlain, at least in the broad strokes. But yeah, it's like certainly seeing the effects of, certainly seeing the effects of these rising temperatures. Thanks for the question.
We have another question here. Thomas says he's read in several sources recently that Arctic temperatures have been increasing about 4 times more than the global mean. Do you know the range of years used as the base as the precise ration of Arctic changes to the global mean, or can you suggest a reference?
So I'm busted, Thomas, because this is a paper I'm supposed to be writing right now. The sources, I was on the presentation that got written up about in December, which you may be seeing the articles from, and yeah, so we mostly looked at warming in the past 30 years for that, because really warming has been quite linear and easily represented by straight lines, and when we've done this calculation with really looking carefully at the uncertainty as well, and we see a range of about 3 to 5 times more than the global mean, and yeah, hopefully that will be a reference out sometime in the next 3 to 24 months, depending on how quickly the publication process goes. But yeah, thanks for the question, and yeah, happy to share more when things are published.
Okay, great. So we're just about a minute left, so I'm just going to wrap it up. But as Nathan said, if anybody has any more questions, please feel free to reach out. I hope that everybody will join us again in 2 weeks. May 18th is going to be our last EI Live K-12 session of the spring semester. And we're going to be looking at a history of the Hudson River, how it's developed since the ice ages, and how human beings have made changes to the river over time. So we'll send out the recording to this session afterwards, probably in the next couple of days. And yeah, thank you so much to Nathan, and thank you to everybody who joined us today.
Thanks, Adrian, and thanks for the great questions.